Greetings everyone, it's been a while. Today I'm going to show you how to read the contents of an RFID tag on a bamboo spool. To do this, you're going to need some sort of high-frequency RFID reader like the ProxMark3. If you already have a different type of RFID development kit that can read high-frequency tags, you're more than welcome to use that. But the ProxMark3 is really popular, really cheap, and easy to get your hands on. So that's what I'll be using. This video is not just about what buttons to press to read an RFID tag, but instead I want to focus on what's happening behind the scenes so that way you understand how RFID works if you're not already familiar. I'll be covering things like keys, UUID, encryption, RSA signatures, and other things that might sound a little bit scary if you're not already familiar with RFID. There's a ton of RFID tags out there, but most fall into the category of either low frequency or high frequency. And there's a ton of types of high frequency tags too. However, there is one type of tag called MIFARE, which is so popular that if somebody's saying that they're using a high frequency tag, they almost always mean that they're using a MIFARE tag. And in our case, that's exactly what we're using. A MIFARE 1K 13.54 MHz RFID tag. These tags can hold a whopping 1 kilobyte of information, which makes it super useful in the 3D printing world for holding things like materials, color names, and other information that your printer might need to know. When you load a spool that has an RFID tag onto an AMS, it reads the tag and tells the printer information about your filament. Before we start reading tags, you're going to need to set up your ProxMark3. Now, I'm not going to cover that in this video because it seems like this keeps evolving over time, and I'm sure that this video would be out of date in no time. Now, I don't know all of the lore behind the ProxMark3 firmware, but from how I understand it, the Iceman fork is the most popular. I think the original ProxMark3 firmware got abandoned and then Iceman took over or something like that. Anyway, the wiki has everything that you should need to get started on this, and I followed these little installation instructions. I'm running on a Mac, so I followed this guide right here to make sure that I could use brew to install all the tools that I needed. If you set everything up right, you should be able to open up a terminal window and type in PM3, which should run the ProxMark3 software. The most important part is that the software on your computer and the firmware on your ProxMark3 match. And my computer is yelling at me for that. If your computer is yelling, just type in exit and then type in PM3/all, which should update the firmware of your ProxMark. All done, have a nice day. So now normally, if you were to clear this and then run PM3 again, it should tell you that your firmware matches, but from what I was reading online, there's a weird issue with Mac where even though the version for all of these three things line up, it still yells at you, but this is the important part, is you want to make sure all three of these numbers are exactly the same. This software is designed to work with all sorts of RFID tags, so if you ever type in something wrong and hit enter, it's going to tell you commands that you should use instead. Now, pretty much everything that we're going to deal with is inside of this HF command, which is high frequency commands. If we were using low frequency, we'd use LF. So anyway, we'll type in HF and then we'll type in nonsense again here, and it will tell us some high frequency commands that we can use. Right down here, we see one of those commands is search. So we could type in HF search. Now before I put enter, I'm going to put the RFID tag on the reader. And now we hit search and we'll see if it can find it. And there we go, we can see right here that it identified a MIFARE tag. We can also see other information about the tag, such as this UID, which we'll come back to later. The output of search also tells us to use HF/MF commands, and if we scroll up, we can find it right here where MF stands for MIFARE RFIDs. This will be all of the MIFARE specific commands. So now let's type in HF for high frequency, MF for MIFARE, and then we'll type in gobbledygook to see other commands. If we scroll up, we can find one called dump. That seems pretty useful, right? Let's try it out. We'll do HF for high frequency, MF for MIFARE, and then dump. And before I hit enter, I gotta put the tag on the reader again and hit enter. I'm just gonna hold it here and let's see how it goes. Oh no. You didn't think it would be that easy, did ya? Before we go any further, we're gonna actually have to talk about how information is actually stored on the RFID card. I mentioned earlier that this is a MIFARE 1K card, which means that it can hold 1 kilobyte of information. But how is that stored? The tag is split up into 16 sectors, from sector 0 to sector 15, and each sector is split up into 4 blocks. And each block has 16 bytes of information. I wrote each byte in hexadecimal format here. The last block in every sector is special. Block 3 always contains encryption keys. It's actually split up into 3 parts, which is key A, key B, and then access bits, but that really doesn't matter for this. For example, if we try to read Sector 10, Block 1 without a key, or rather the default key, then we're going to get all of those authentication errors that we saw earlier. But if we try to read it with the correct key, then we can access the information. That means that we need to figure out what those keys are. Unfortunately, we can't just read the last block which contains the keys because you would need the key to read that block in the first place. However, we do have something that does know the key. For example, when the AMS wants to know what color a spool is, it can ask the RFID tag to read Sector 1, Block 1, which contains color information. In order to read this information successfully, the AMS has to know what the correct key is for this sector. And if the key is correct, the tag will return the information at Sector 1, Block 1. Now, wouldn't it be cool if we could just listen in on that conversation? Well, we can. We just put our ProxMark3 in between the AMS and the spool. This means any communication from the AMS to the spool or from the spool to the AMS has to go through the ProxMark, which can then be recorded and saved to a log file. Then we can pull out any information that we care about, which in our case would be the key. I'm using an AMS Lite, and right on Bambu's own website they show us what the RFID coils look like on the inside. To be honest, I didn't even know you could do an RFID antenna like this, but I guess you can. This means that no matter how we orient the spool, the AMS Lite's going to be able to read the tag. The reader is a little bit different in the AMS Classic. In this case, there's readers inside of these two circled fins. The RFID reader in the leftmost fin can read from bays 1 and 2, whereas the other one can read from bays 3 and 4. For the AMS Classic, the orientation of the spool does matter, so you'll have to line up the actual tag with the fin. Now we just need to make the AMS read from the tag. By looking at the screen on the printer, we can see that just loading up a spool doesn't actually cause the tag to be read. The tag isn't actually read until we put some filament into the feeder. And here we can see that after a few seconds, the printer can identify what filament we loaded. I'm going to take apart one of these spools and rip out the RFID tag. Now we can trick the printer into thinking something's loaded by taping the RFID tag somewhere where the sensor can read it, and then loading in a strand of filament. And if we look at the screen on the printer, it thinks that we loaded up a spool of orange PLA. And now we just need to put our ProxMark in between the tag and the AMS. I'm doing this by taping a tag directly to the ProxMark, and then taping the ProxMark to the AMS. Very professional. Now it's time to record the communication. If we type in HF, we'll see all the high frequency tags, and right here at the top there's something called 14A, which is ISO 14443A RFIDs. Honestly, I wish I knew why this mattered. I believe MIFARE is probably a subset of this, but this category is what has all of the sniffing commands. So down here we're going to type in HF14A to see all of the commands, and here we can see sniff as one of those options. Now we can type in HF for high frequency, 14A for the card type, and then sniff for the command, and I want to see all of the arguments that we can do, so I'm going to do -- help. We're actually going to use the command from this example right here because there's a lot of data when we're trying to sniff, and we don't want to just be reading all the time. We instead want to trigger it when something actually happens. Logging nonstop would eat up so much memory that we would only be able to get a couple of seconds worth of readings. So once again, let's type in HF for high frequency, 14A for the card type, sniff for the command, and then -C and -R to make sure we're triggering it instead of reading nonstop. Now we can see that we've started to sniff data, and we can press the button on the ProxMark when we're done. Now I'm just going to load a strand of filament into the AMS so it actually tries to read the tag. You can see some LEDs blinking on the ProxMark while it's recording information. And as soon as we're done, we'll press this tiny little button right here to send all the data to our computer. And if all went well, we should see a trace length here, and in my case, I read 3,306 bytes worth of communication. Now we need to decode the information in a way that makes sense. To do this, we'll use trace list. Now we want to check out some arguments, so I'm going to use -- help to list those out. And you can see here that we have a lot of examples. In our case, we're using a MIFARE tag, so we want to use the -TMF arguments to make sure that we're decoding this as if it's a MIFARE handshake. So let's give it a shot. We'll type in trace, list, and then -T for type, MF for MIFARE. Unfortunately, I got to make my text a little bit smaller because this is impossible to read. There we go, that's a little bit better. Hey, look at that, something says key. I'm going to scroll all the way to the top, and we're going to figure out what all this means. Right off the bat, we see that there's a key identified. If we scroll down a little bit more, we can see this little message here saying nested authentication detected. We'll come back to that. If we keep scrolling through, we can just see that there's a lot of information that doesn't seem to make any sense. And near the end, we can see a key again, which is actually the exact same key we saw earlier. Let's hold on to this key. I'm going to copy it and save it for later. At this point, you can remove the ProxMark from the AMS. It won't hurt anything to leave it attached, but I just wanted to let you know at this point we're no longer sniffing communication between the AMS and the spool. Instead, we're talking directly from the ProxMark to the RFID tag. The AMS isn't doing anything anymore. Before we do anything with that key, I want to look at something that's called HF for high frequency, MF for MIFARE, and then we're going to look through these commands here. And if we scroll up, we're going to find something called FCHK, which checks keys fasts, targets all keys on card. And we're going to use this to check how many keys we've figured out. So we'll once again do HF for high frequency, MF for MIFARE, and then FCHK for fast key check. And then we're going to do -- help so we can get some more arguments. One of the arguments that it lists out is this --1K, which is used for MIFARE Classic 1K cards. It's kind of cool to see here that this also supports 2K and 4K cards as well, but we're using the one that has 1 kilobyte, so we're going to use --1K. We don't need anything else yet. So let's try this out. We're going to type in HF for high frequency, MF for MIFARE, FCHK for fast key check, and then --1K to say that we are using a 1K version of MIFARE Classic. Now we're just going to have to wait a little bit. Okay, now we're done. What this ended up doing was loading 59 commonly used encryption keys and then trying them all out. And in this case, none of them were a match. These 59 keys that it loaded are from a dictionary, which is just a list of keys. And we can make our own dictionary. And if we glance back up here, we can see a -f argument, or -- file, which will be the file name of a dictionary. So let's create a dictionary with all the keys that we find. All of the dictionaries live in a folder called Dictionaries wherever your ProxMark3 software is installed. You're going to have to hunt down your own installation directory because this is operating system specific. My installation directory is the user folder, local, and then seller, which gets you to all the homebrew applications, and then ProxMark3, the version number, share, and then finally ProxMark3. So this is the folder that we want to save all of our dictionaries to. Remember this key from earlier? Let's save it as a dictionary. I'm going to go to File and then Save. I navigated to my ProxMark3 installation directory and then clicking on the Dictionaries folder, and now I can just give it a name, and I'm going to call it Mitch. Oh shoot, I forgot it's supposed to be mitch.dic, so it knows it's a dictionary file. Let's test out some keys using our own custom dictionary. We'll do HF for high frequency, MF for MIFARE, FCHK for fast check keys, and then we're going to do --1K to say that we're using a 1K MIFARE card, and last but not least, we'll use -F Mitch to say that we're going to use our own custom dictionary called Mitch. Huh? What, Okay, I figured out my error, and I'm going to show you how to do it correctly this time. I'm going to create a new file here, copy this key, and then I'm going to go to File, Save, and I'm going to still save it in the Dictionaries folder, and I'm going to call it mitch.dic, but the problem was that I accidentally forgot to do an extension last time, and it added .txt to the end of my file name, so I really don't want that. My old file name was not mitch.dic, which is what it was looking for, but instead it was mitch.dic.txt. So I'm going to leave this box unchecked, I'm going to hit save, and now I have a file called mitch.dic. We can retry the command now by pressing up to get to our previous command and hitting enter. Awesome, so what we can see here is it loaded the default 59 keys, but also our one custom key from our own dictionary file. And now it's done, and look at that, we have a key table. This table should make a little bit of sense. Here you can see that we have sectors 0 through 15, and we've successfully learned the key for sector 0. That means we can finally read info from sector 0. Unfortunately, we don't know the keys yet for sectors 1 through 15. Now let's find the rest of the keys. Do you remember when we ran this trace list command and got all of this nonsense? I pointed out that there was this nested authentication detection. I'm not an RFID expert, but I'm pretty sure this means that one key depends on a previous key. So now that we know the first key, we can use that to find out the second key. It's telling us to use this brute force command with all of these arguments in order to find out the next key. I'm going to copy all of this information, then I'm going to stop at the name of this tool right here. Right click and copy. Now if we go back to the folder wherever your ProxMark3 is installed, we can find this folder called Tools, and in there is this MFNONCE brute, and that's what we're looking for. Okay, so I'm going to open a new terminal and leave the old one open in the background, and then I'm going to go CD into that folder that we were just looking at, which is user, local, seller, ProxMark3, the version number, share, ProxMark3, and then tools. I'm going to adjust this so we can see both windows here at the same time. I'm going to copy this command from here. / is how you run something in Mac and Linux. I'm going to paste that command in and hit enter. And now that it's done, it brute forced this new key for us. How nice. All right, at this point, I'm going to copy this key. We're going to go back to our dictionary file, and we're going to paste this as a new line. We've discovered 2 keys. File, save to make sure that we save it. And now we're going to go back to our Proxmark window. We're going to run the same command that we did a little bit earlier, which is right here. It's high frequency, MIFARE, fast key check, 1K, -F Mitch to use the Mitch dictionary, which now has 2 items in it. Let's see what we get. We can see that we're loading 2 keys this time. And look at that, we have our second key discovered. We can now read sectors 0 and 1. By now, you've probably realized that we're on the hunt for new keys. Every time we find one, it will help us discover the next. We're just going to keep repeating this trace list command until we find out more keys. However, this time we're going to add -F Mitch, which will use our new dictionary. This will help us decode information that previously didn't make sense. Ah yes, I forgot. Every time you try to display this key table, it erases the log that we previously had. If this ever happens, it just means that you need to resniff the data. To resniff communication, we just need to tape that ProxMark back to the AMS and then run the command HF for high frequency, 14A for that type of card, and then sniff for the command, and then the arguments are going to be -C and -R to make sure we're not reading continuously. Now we just need to unload and reload the filament so that way the AMS will try to read the RFID tag again. Then press that little button on the ProxMark to stop capturing. And now we can go back to our tracelist command. Don't forget that -F Mitch so that way you're using the new dictionary. All right, let's scroll back to the top. I'll move our existing keys over here. All right, so once again, you can see that we've already discovered this key that starts with 6E, which is our first key. And if we scroll down, we can see the second key as well, 4C. Now, if we keep going down further, we see this right here. It says nested probable key, and it starts with 0B. This is new, so we're just gonna yoink that and paste that in our dictionary. And let's scroll down a little bit further to see if we discovered anything else. So look at this, another nested authentication detection. We're gonna open back up that other terminal that was already in our tools directory, and then we're gonna copy this command, and we're gonna paste it in here with a / in front of it. And we've discovered another key. We'll copy that one and paste that into our list as well. Let's keep hunting to see if anything else popped up. Down at the bottom, we're seeing our 6E key again, which we've already discovered. Let's save our dictionary. And now we've discovered 4 keys. At any time, you can rerun this fast key check again to see if those are actually valid keys, but it doesn't really hurt to have any bad keys in your dictionary. They just won't work. But just a reminder, if you do this, then you're going to have to re-sniff that data, so I'm going to skip this for now. So we're just going to repeat this trace list again and make sure that we have our Mitch dictionary, which now has 4 keys, and let's see if we can find more. You know the drill. We're going to hunt through 6E we've already seen, 4C we've already seen, 0B we've already seen, 90, that's one of our new ones. Oh, what's that right there? We got another brute force one. We'll copy this and paste it down here and grab that key. We'll keep looking through, and we're at the end, and there's that 6E key again. Now we rinse and repeat. Let's save, and then hit up to repeat that command again. I'm just going to speed through this. I think you get the idea. Okay, at some point you should hit 16 keys. Now, there's a chance that you might have gotten a dud one in here or something, so don't stop when this hits 16, but rather stop when you can scroll through this entire thing here. I'll go to the top, where you can scroll through this entire thing and all of the keys on the right-hand column say that they're found and that there's nothing in the middle that says probable key or brute force or anything like that. So at this point, I've discovered all of the keys for this tag. I shouldn't see any hanging out in the middle. I'm just doing one double check here. Yeah, it looks like we're good. Now that I'm pretty sure I discovered all the keys, I'm going to rerun the key check program just to make sure I did. I'm going to type in HF for high frequency, MF for MIFARE. It's going to be FCHK for fast check key, --1K to make sure we're using 1K MIFARE cards, and then -F Mitch to use our Mitch dictionary. So at this point, we're communicating with the RFID tag, and we're trying out those 16 keys to see if we can actually unlock those sectors. And there you have it. We've discovered all 16 keys. If any of these are missing, you need to go back and repeat the previous step. This means we've officially figured out the key to read every single sector of this RFID tag. And before someone says it, yes, I know you can automate this process if you write a script. I just wanted to show that you could do this even if you're not using fancy scripts. Now it's time to read off all the contents of the tag. If you remember, one of the first commands we tried was HFMF dump, but running this gives us all of these authentication errors. Yuck. But this time we're back and we have keys, so we'll do HFMF dump --help to see arguments. Now this is annoying. We actually have to use -F to specify the output file name of the dump file. Up until this point, -F meant dictionary. And we can see -K is a key list. Now note, this is a key list and not a dictionary, so we actually have to convert the dictionary to a key list. To save the keys to a file, we're going to use the same program that we did to verify the keys, which is HF for high frequency, MF for MIFARE, and then FCHK for fast check, --1K for the 1K type of cards, -F for our dictionary file, which is Mitch in this case, and then we're going to add --dump to the end to save it to a file. And now we wait. There we go, our keys have now been saved to this .bin file. Since I saved it to the default location, I can just grab the file name. Now we can use this key list to dump the data. So we'll do HF for high frequency, MF for MIFARE, and then we're going to do dump -K for the key list, and I'll paste that in, and then we can hit enter. This time you can see we're not getting authentication errors, but instead we are successfully reading all of the sectors, and it feels very good. And there we go, the entire contents of this tag have been decrypted and saved to this bin file. And if you're curious, you can copy this file, exit out of the ProxMark program, and then run hexdump and paste in that file, and it will kind of let us view it in hex format. Actually, I meant to do hex edit, which shows us some more information here. The main difference is that the middle column here is all the hexadecimal stuff, but on the right-hand column it shows it also in ASCII, which is kind of like human-readable text. Most of this looks like jibber-jabber, but some of it you can pick out things like dates or maybe timestamps. This says PLA, I think I know what that means. And this is PLA basic. Instead of trying to reverse engineer this on your own, you can instead go to GitHub and look up the RFID Tag Guide by the Bamboo Research Group. For example, you can see that block 5, also known as Sector 1, Block 1, has the last few bytes are the hex code for the filament. This is an open source project, so there's still some unknown data, and if you do some reverse engineering on your own and you figure out what this is, you can always contribute it to this project. There's one more thing that I would like to mention before someone tries to modify this to create their own tags. The last 4 sectors, or the 256 bytes of information, is actually a 2048-bit RSA signature. What does that mean? At a very high level, this is how signatures work. You have some data, and then the signature is what tells you that that's real, good, genuine data that hasn't been tampered with. For example, these RFID tags have things like color, diameter, material, and all sorts of other things. Signatures look mostly random, but they let us know that that's real, authentic information. If you were to change even just one letter, the signature would look completely different. If you change the data without changing the signature, it's considered invalid. The BambuLab AMS checks these signatures and will throw out any RFID tags that are considered invalid. That means that you could copy a tag exactly as is, signature and all, but the only people that could modify or create a new tag is BambuLab themselves, because they're the only people with a key that is able to create the signature in the first place. RSA signatures are rock solid. If there was a way to break them, then our entire world would basically collapse. Things like Bitcoin rely on it. And if that makes you upset, well, you're not alone. The way I see it, there's about 2 or 3 solutions. The first is that BambuLab could allow invalid signatures. By this I mean that the AMS could still do a signature check, but if it ever comes across a tag that doesn't have a valid signature, instead of not using it altogether, you could just use it and mark it as non-genuine. That would still allow Bamboo printers to tell the difference between a genuine BambuLab spool and a third-party spool. Option 2 would be to allow filament manufacturers to digitally sign their own spools and then register that key with BambuLab. That would mean there could be more than one manufacturer that could digitally sign genuine spools, and you would be able to see who signed them. So once again, BambuLab could certify their own BambuLab spools, and then there could also be some trusted third parties that are also digitally signed. And last but not least is to scrap all of it and create an open source RFID protocol. This is actually something that's already been started. The whole idea is to create an open source protocol that doesn't have a signature. Now, of course, the firmware of the 3D printer would have to support this, but this could be more scalable, as it's highly likely that more printer manufacturers are going to start using RFID in their projects. Something like this would help make sure that one RFID tag can work with all of the printer manufacturers. This video took forever to make. It was really tedious. If you found even just a little bit of it useful, it would mean the world to me if you subscribed. That would also be the kick in the butt that I need to create the next video on how to write RFID tags. Well, see ya.